Now sometimes where you put them makes it easier to see the result, but there are two shapes where it matters where the lone pairs remain, and that's the Trigonal Bipyramidal and the octahedral. Other than that, you can put your atoms on any one. In a case like this where you got some lone pairs and shared pairs, you can put them on any one you choose. I mean, you have to put, of course, the double bonds where the double bond was, right?
On the pyramidal and the
Trigonal pyramidal.
Does it need to be straight up, like?
Well, no, in a trigonal pyramidal, lone pairs need to be on the equator.
Okay.
So that's the three around the middle. Mm-hmm. Okay. On octahedral, it only matters if you have two or more lone pairs. Okay. Because then you want to put them on opposite sides of the structure, and it really doesn't matter where. It's really easier to see the result if you put them at the poles, but it doesn't really matter where, as long as those lone pairs are on the opposite sides of the structure.
So they could be anywhere on it.
Anywhere, as long if you have an octahedral electron pair shape and modified electron pair shape, it only matters that you put that whenever you arrange all your atoms on that structure, if you have more than one lone pair, you have to have the lone pairs as much as possible on opposite sides. Okay. Now, there are times when you can't get them completely on opposite sides. That's okay. But you put as many as you can on opposite sides. Okay. So it's really just a matter of reasoning it out. All right. So now this is still trigonal planar because I still have three arms equally spaced. But because we have both electron sets and atoms on here, we're going to call this a modified electron pair shape.
Will it always be like considered modified if we've done what we just did?
No, because sometimes we get rid of all the pairs, we'll be already at the molecular shape. If when you get to this step, if you've got both atoms on the outer edges, around the outside, and electron pairs, if you have both of those, then it's a modified electron pair shape.
So if two...
If there are no pairs of electrons anymore, you've got the molecular shape. Okay? If you do all the step-by-step process that I'm teaching here. Okay? All right. So the next thing then is to take and redraw exactly the same thing again. Okay? So each time we're going to redraw the only original shape we're drawing is this, and these become modifications of what came before it. Okay? So we're going to put our oxygen down here. I'm going to put the chlorine over here, and I'm going to put the lone pair up here. Okay? Did exactly the same thing, same drawing. Okay? So since these two are the same, the next step then is to take off the lone pairs. Remember, that's what we need to get to a point where we have no more lone pairs on there. Okay? So we take that off, and we have a molecular shape. But you have to go through the step. If you don't go step, step, step like that, you'll end up with what students do is they'll skip the step here, or they'll skip writing the lone pair and they'll write a linear shape. Yeah. You see? Now, again, we have some students who can do this in their head. They probably don't need to do all the steps. But if you get to the really complex stuff, they probably need to do those too. But if this is not something that just comes readily to you, you do all the steps, you're probably going to get the right shape. I'm not saying you will definitely, but your percentages are really high. Okay? So now we got a shape. I bet you can tell me what that's called.
A bent.
Bent. There you go. See? Once you get there, it's fairly easy, isn't it? And it's called a molecular shape because no longer do we have any lone pairs.
But it will only be bent if there's two, like off it. Like if there was like.
Well, not all atoms that have just two outside are bent. This is bent because it makes an angle right there. Okay. All right. So for instance, if we had something that looked like this, well, that's linear.
Oh, because it's not.
Yeah, it's only bent because we bent it.
So that would be as if like you had two lone pairs and you had erased those.
Yeah, well, no. Don't get too complex with it. But if there were two lone pairs up here, it would still be a bent shape. Water does that, okay? Because the lone pairs actually take up space around that central atom and push those bonds away.
So that would have been like if you didn't have any...
Well, this is what you get when you get carbon dioxide.
Okay.
So carbon dioxide starts out with a double bond going this way and that way.
So that's just a linear molecule?
That if it comes out straight like that, that's linear. Okay. And the trick to this, and when I say trick, there's a whole story behind that. But when I say trick, I don't mean that it's like illegal or unsavory or anything like that. It's just like you got to think about it this way. You know, to figure it out. The trick to it is remembering we got to show those lone pairs to show how it bends the shape around. Okay?
I get that.
And we did the balloon model so you could see when you put the balloons together, and you go back and look at that balloon video, you'll see how putting that balloon up here bends that down.
And it goes all the way back to this shape because if you didn't draw it at 120 degrees.
That's right. You got to start at 120 degrees, and then this is still 120 degrees when you get through with it. Technically, it's actually slightly less than that, but we don't get into that too much in here.
Yeah.
Because that's probably for way on up in college, organic something. Okay. That makes sense? So step by step, do all the pieces, and you're fine. So since I mentioned trigonal bipyramidal and octahedral, let me just show you real quick what I'm talking about there. So trigonal bipyramidal, I'm going to use A and B here as atoms, okay? So here's our central atom A. And let's suppose I have trigonal bipyramidal. That's where I have 5 sets of electrons around a central atom. So I'm going to start out with 5 sets of electrons here. So that means I've got to have one coming out like that, one that's swinging out toward you. Remember, the triangles mean they're swinging out away from the paper toward you. Okay? And then the dotted lines, have you taken art?
In middle school I did.
Okay. Well, do you know what perspective means?
Yeah, like the way you are like seeing like the certain.
Yeah, so if you look at the back of the room here, it's like it's like the walls are getting smaller and smaller as you go back, right? Well, when you draw that, you got to draw it that way.
Yeah.
So that's called perspective. Eventually, I can take all the corners in the room, and if I drew a line until they would actually intersect somewhere way back somewhere. Who knows how far back? Okay. If I were to draw this room, I'd end up with those lines in the corners, in the ceiling corners and the floor corners. The ones on the sides here going back to the back, they would all intersect.
Because they're going in ever so much.
That's called the vanishing point. Well, chemists aren't that great on ours, okay? So we come up with a simplified way of doing that. We're just showing this is coming toward you, that's going back behind without being too complex about it. Make it faster too, okay? And all chemists know that's what it means, okay? So that's what that means. So this is trigonal planar. You've got 2 electrons in the polar positions, like if this were a globe, north and south pole. And then around the equator here, these would be arranged 120 degrees apart around the equator and 90 degrees from the poles. Okay? All right. Since there's more space on the equator positions, because there's 120 degrees from one angle to the next, lone pairs need to remain here if I have them.
Okay.
So let's say I'm going to put 4 atoms on this. Okay? And I'm going to leave 1 lone pair. Okay? Then I need to have 1 atom here, 1 atom, and it doesn't really matter. I just have to have a lone pair somewhere on the equator. It's a little easier to see what I'm doing if I put them out here like this. All right, and the lone pair would be over here because there's 120 degrees available around there.
But you could have put it on this one right here.
I could have put it over here. The lone pairs could have been here or here. Anywhere on these equator positions. They're called equatorial positions. Okay, and then when you do the next shape, you take those off, and we get something called irregular tetrahedron.
Okay, but we haven't done that yet, right?
No, but if you look in the handout, that's what it says. So if you get one of those on the test, you got to know that's an irregular tetrahedron. So this shape without that on there, irregular tetrahedron. Okay? That's what that would be. T-E-T-R-A. T-E-T-R-A. Tetrahedron. I wish when they teach you squares and spheres, squares, not squares.
Like octagons and.
Yeah, all that stuff when they teach you. I wish they would teach tetrahedrals.
That would make it a lot.
It would. Yeah, it would. Tetrahedrons. It's a tetrahedron is a geometric shape that has triangles on every side and has 4 sides. That's a tetrahedron. T-E-T-R-A means 4.
Okay, I think I can see it in my head.
Okay. All right. So it's like a 3-sided pyramid if you include the bottom.
Okay.
Okay. So tetrahedron just means. So if you include the bottom, that's 4 sides, each with a triangle. Okay. All right. So in this case, we need to have lone pairs need to be here. If I had more than 1 lone pair, I'd put them out here somewhere. Okay. Or I might put the B over here and both lone pairs over there. Okay. Now in an octahedral, then we've got the 2 polar positions, but we got 4 positions around the equator.
Does tetra mean like 4 or something? that like
Tetra means 4.
Okay.
Okay. This is octahedral because there's 8 sides on this. Okay. All right. So if we have our lone pairs out here on this, and I've not darkened in these triangles, but you kind of see where I'm going, I hope. Okay. All right. If I have one lone pair, it really doesn't matter where I leave the lone pair. Okay. It's easier though to tell the resulting shape if I put the lone pairs in one of the polar positions, because then you can see the pyramid that results pretty easily. But if I have more than one lone pair, I need to have them on opposite sides. And because they take up more space, they tend to arrange themselves as far apart than as they can get from each other, as opposed to being as far apart from the bonds. Even though there are 2 electrons in all those positions, the lone pairs want to be as far apart as they can get. Okay? So that's the only thing to keep in mind about that. All right? Do you want to practice some more, or you think you're pretty solid?
Can I practice on like the drawing, like?
Oh yeah, we got to do we still have to do the shape of the bonds themselves. Okay, we got to go back and do that. Okay, so then we're going to go back to this drawing we did originally, because I want to go back to these drawings right here, the Lewis dot and Lewis formula. Okay, because I have both a single bond and a double bond on here. Okay, and that's one of the reasons I chose this molecule, because I got both of those there. Okay, so between the nitrogen and the chlorine, there's just a single bond. And a single bond is always going to be a sigma bond, okay? And that's because that bond it's directly on line between the 2 nuclei. And we kind of pictured a single bond or a single bond, both of those, being like a wiener on a stick, okay? So it's just like we had, and I'm going to just draw, let's do this in red here. Suppose I've got a straight line. This is our line between the 2 nuclei. Now that's not real, that's just imaginary. I'm doing it in red so you can see it. And then we're going to stick a wiener on that stick. Okay, and that's our sigma bond.
So that represents the 2 electrons.
The 2 electrons will be, what we had originally was we have a nitrogen with a hybridized orbital and a chlorine with a hybridized orbital. Okay, and those hybridized orbitals, we slide those together and they overlap. And when they overlap, we got a bond. And it doesn't keep that sort of fatter shape. It sort of narrows down into this wiener shape. Okay.
So what in this represents the hybridized orbital, or is there nothing that represents?
Well, yeah, these don't represent any kind of hybridization. Okay. You just have to know there is hybridization there.
There's one for each, if it's a single bond?
Well, any sigma bond has to be a hybridized orbital. Any lone pair has to be back it up. Any single bond has to come from hybridized orbitals.
Okay.
Okay, any sigma bond has to come from hybridized orbitals. So this had to be a hybridized orbital. That had to be a hybridized orbital to form this sigma bond.
So that sigma bond is where they overlap?
Yep.
Okay.
So you have to get sigma bonds from hybridized orbitals. But it's also true that lone pairs have to come from hybridized orbitals. Okay? So on this nitrogen, there's got to be a lone pair up here. Okay? And that's that single balloon shape we did with the balloons. And that's a hybridized orbital. It doesn't form a bond because it already has 2 electrons in it. Doesn't need a bond. Remember, you can only get 2 electrons in an orbital anyway.
Yeah.
The only reason that these sigma bonds, these hybridized orbitals here overlap is because they both have 1 electron in them, and they overlap so you can get 2 in there, because an orbital with 2 electrons is more stable.
Oh, so you go back to like this drawing right here. They like shared, or no, this one they shared those.
Yeah, well, what we're showing here is we're sharing 4 electrons, okay, and we're showing 2 electrons here.
Okay.
So this really has very little to do with this.
Okay.
Because this is just how do we get them to work out, and this is what does it actually look like when we get there.